Hello, I'm Stephen Hardy, Editorial Director of Broadband Technology Report. Cable operators preparing their networks for DOCSIS 4.0 and the support of 10G services are evaluating a new generation of transmission elements, including 1.8 GHz amplifiers. But with new technologies, potentially come new concerns as well. And to help address such concerns, I'm joined by Steve Condra, Senior Director of Business Development at Teleste Intercept. Steve, one area where we've heard some talk regards whether the new generation of 1.8 GHz amplifiers is particularly power hungry. Is there any truth to this?
Yeah, I'm glad you asked, and thanks for having me this morning. It would seem to reason that the 1.8 gig amplifier upgrades are going to require a lot. They're going to enable a lot more spectrum, and at the same time require a lot more RF power. If you imagine we're getting 40 to 50% more RF spectrum, and the attenuation at 1.8 gig through coax is a lot higher. So the RF power requirements for an amplifier are much higher. However, we've been able to carefully select components and take advantage of the efficiencies of the next generation silicon components and use that to get near parity to the previous generation 1 gig products. And as you can see from the graphics, there is very little difference between the old version 1 gig products and the new version 1.8 gig products as far as actual power consumption.
So what you're showing is useful power. What about total power?
Yeah, so the total power takes advantage or takes into consideration both the useful power to power up the amplifier as well as the reactive power that is caused by differences in phase of the incoming current. And you'll notice in almost all data sheets is that vendors will list both the power consumption of the amplifier, but also the current draw at each individual voltage, usually in 5-volt increments. And that will represent the total power consumed by the amplifier. Those can be dramatically different. If you took the useful power and divided it by the total power at any of those individual voltages, you will see that normally products in the past have run between 70 and 80% power factor, which is the ratio between useful power and total power. What we've been able to do is use a technology called power factor correction, which enables us to align the phase of the incoming power so that useful power and total power are nearly equivalent. And so we've been able to improve that power factor from 70 to 80% up to 99% or very closely to 100%. That, by definition, will do two things. Number one, it will make the current draw predictable, and current draw will now just be voltage times current, or VA, for the useful power, and it will also make it less. You will see somewhere between in the neighborhood of 20 to 30% less current draw, or less maximum current draw at any of those individual voltages.
And how should operators evaluate the difference between useful power and total power? And what effect does this difference have on network operation at 1.8 gigahertz?
So first of all, the current draw will be very predictable. Without power factor correction, current draw can change with time. With power factor correction, two things happen. First of all, the power factor becomes almost unity, in other words, almost 100%. And second of all, the power consumption, or the current draw, is less. As a result of less current draw, there's less power consumed from the power company and obviously a smaller bill. Over time, that savings can be somewhere between 5 and 25%. But more importantly, what happens is now we have freed up current draw from the network power supplies that can be used for other parts of the network, whether it's plant extensions or whether it's adding Wi-Fi networks out in the field. Other appliances are now available to draw from the network power supplies that already exist. In addition, there won't be any need for additional network power supplies. There won't be a need for additional permits for additional network power supplies. You'll be able to live within your budget and have some budget left over for other things in the future.
Can we add up some of the savings that you've just discussed?
I can. I mean, the first is the predictability of current draw. And the second is that if your network power supplies are performing adequately today at 1 gig, we should be able to upgrade to 1.8 gig and still maintain the same power grid structure that you have today. So no need for additional power supplies, no need for upgrading existing power supplies, no need for additional permits to add power supplies. But in addition, you should see somewhere between 5 and 25% improvement in your actual power bill from the power company. So despite being green and sustainable power and getting a lot more bits per watt and a lot more throughput for your dollar of power bill, you also will have predictability in how those power supplies will react.
So with all of this taken together, what can we conclude about the power requirements of 1.8 gigahertz amplifiers?
Well, I think it's been an industry-wide accomplishment with a huge increase or a huge improvement in the number of bits, the number of throughput we can get through coax at the same amount of power draw as we had previously, like we saw in the original chart showing the useful power. But in addition to that is the ability to use power factor correction to make current draw more predictable and less, and not have to live with both a maximum current draw as well as a higher power bill.
Thanks, Steve. So it seems the power consumption of 1.8 gigahertz amplifiers is at least one area where cable operators can lay their concerns to rest, which undoubtedly will help enable such operators to move forward with their network enhancement plans with greater confidence. For Broadband Technology Report, I'm Stephen Hardy.